Welcome to the second lecture related to the topic numerical integration. First, let's summarize what we covered in the previous lecture. Remember the problem at hand we want to solve. Our goal is to compute the definite integral of a function f of x in a given interval a, b. And as we explained in the previous lecture, for different reasons, it's not possible to compute this area analytically. So we saw in the previous lecture different approaches to do this in a numerical way. For example, we saw what are called the simple rules, the rectangle rule, the trapezoidal rule, and also Simpson's rule. And the main idea behind all of them is the following. We will fit this function f of x with a polynomial, and then we will compute the integral of the polynomial exactly, which is straightforward. The main idea is this one, and we saw for the different methods, for example, for the rectangle rule, how this polynomial in this case is a degree 0 polynomial, and we can find, for example, this formula to approximate the exact integral. Remember that for the rectangle rule we have a variety of methods depending on which point we use to select the height of the rectangle. For example, this one is called the left rectangle rule because point A, which is the left side of the interval, is used to compute f of a, and that's what defines the height of the rectangle. Then we can approximate the integral using the length of the base of the rectangle times the height of the rectangle, and that's an approximation. Then we saw the trapezoidal rule, which uses a degree 1 polynomial to fit f of x just with a straight line using the values of the function at points a and b. In the previous lecture we saw that we did the calculations and we found the formula that must be used to compute approximately the integral using the trapezoid. Then we saw also Simpson's rule, where we use a second degree polynomial, a parabola, to fit the blue function f of x with this black line, which is a parabola, that goes through the points a, b, f of b, and also the midpoint between a and b. We did also the calculations in this case, and we found the formula that must be used to approximate the integral using this method. So the summary of the previous lecture could be this slide. We know how to compute approximately using these different formulas the approximate value of the integral. However, we don't know how much error we are doing using these formulas. Of course, this is very important. When using a numerical approach, it's always very important to know a bound of the error, to have an idea of how much error we are doing using this numerical, this approximated approach. So today's lecture concerns to bound this error, to know how is this error. So let's see if we can know something about the error. Now, as we said, what we are doing is, for any of the simple rules we saw, we are using a polynomial to fit the function, and this polynomial is always the pure interpolating polynomial. So there is an error when fitting the function with the pure interpolating polynomial, and this error, it's known for us, it's the Lagrange remainder. Now, what we do in this topic is we want to compute the integral of f of x, but as that is very difficult for different reasons, we will compute the integral of the polynomial, and we will use this as an approximation of the exact integral. But you can see here that this is going to be the error that we are doing when approximating the exact integral by this integral. That is what will be missing, yeah? So basically we can estimate, we can bound the integration error by trying to bound to see how we can write down this expression, okay? Now, this is what really it's important to us today. We want to know the expression of this term. Now, recall that when we did the last topic about fitting a function, we saw that the Lagrange remainder, the error that is done by pure interpolation, has this expression. We work a lot with this expression. We did some exercises where we bound this error. Now today we will use this expression to estimate the integral of this error, because that's the integration error we are doing. Okay, so I will try to split the window in two parts. Okay, this one needs to be smaller. That would be fine. Okay. Now what we want to do is, for each one of the simple rule methods, we will start with the simpler one, the rectangle rule. We want to find out what's the formula for the integration error, okay? Now, if I'm using the rectangle rule, I'm approximating f of x by a degree 0 polynomial, and then I have the Lagrange remainder that comes from this pure interpolation with only one data point, okay? If I assume that I'm using the left rectangle method, okay, that means that the constant value used for this constant polynomial is f of a, yeah? Then I will try to write down here what is the Lagrange remainder, okay? And in order to do that, I will use this slide. Now, who is going to be here n? Remember that n plus 1 is the number of data points, and n is the degree of the polynomial. So here, my degree has polynomial 0, is a constant value function equal to f of a. So here I have R0 error, n equals 0. So I have only one data point, which is a, and f of a associated to that point a. So what I'm saying here is that can I write here? I'm not sure. Okay, what I'm saying here is that I only have one data point, x0, which is equal to a. Okay, so that's why x minus a here comes from this Lx, which is only x minus a, because there are no other data points. And then, as n is equal to 0, I have the first derivative of f, at a point mu that I don't know. So at a point mu that I don't know. And then I should divide by 0 plus 1 is 1 factorial, and 1 factorial is 1. So that's the expression that I get for the Lagrange remainder when approximating the function by this degree 0 polynomial. Now, what I want to do is to find the integration error. Remember that the integral is equal to the integral of the polynomial plus the integral of the error. But what we are doing in real application is to just use this part to approximate the exact integral. So this is the integration error. So I need to compute the integral of this term to know the integration error. And that's what we do here, okay? The integration error is equal to the integral of the Lagrange remainder. So the integral of this function we wrote here. Now, here we will use a theorem at this step. We will use a theorem that is called the integral mean value theorem. This theorem says that if you have two continuous functions in a closed interval and one of them you can assure is positive, then there exists a point between the open interval AB, such that the integral of the product of the two functions is equal to some value of the function at a point C that we don't know, but it exists, times the integral of this function that is always positive in the interval AB. Okay, I will post you some references if you are interested in understanding better this theorem. Here I will just use it. Okay, now I know that this function x minus a is always positive between a and b. Yeah, because between a and b, that means x belongs to the interval a and b. So that it will be always bigger than 0. Okay, so I can use this mean value theorem where the positive function remains inside the integral, but the other one can be written outside of the integral, but evaluated at a point that I don't know, but it really lives inside the interval AB. Now here it's a very good place to apply this theorem, because before I didn't know where I should evaluate f prime, neither do I know it now. Yeah, so the situation is pretty similar, but now I was capable to write f prime outside from the integral. So now I can compute this integral. That's very simple. It's a 1-degree polynomial. I compute the integral and I get this expression, which is going to be, this is very important. Maybe you can try to box it, or if you like boxing things, as I say in my lectures, this is something you should box. And it's very important to box together with the fact that I know where psi lives, and it lives inside the interval AB. Okay, so this is what we will call the expression of the integration error for the rectangle rule. Okay, now we will do something pretty similar with the trapezoidal rule. The same idea. I know that for the trapezoidal rule, f of x is going to be fit by a degree 1 polynomial, and I will have a Lagrange remainder, R1, which will look like this. Let's see if this makes sense. If this is the trapezoidal rule, that means that you are using a f of a and b f of b as data points. Yeah, so here my data points x0 and x1 are a and b. So that's why I only have two terms, x minus a, x minus b. As n equals 1, that's the degree of the pure interpolating polynomial, then here I have 1 plus 1, I have a second derivative. Okay, that's why I have a second derivative here. And here I have 2 factorial. Okay, so this is the expression of the Lagrange remainder. And now I will compute the integral of this error. So I will get the integration error. Remember that the integration error comes from the integral of the Lagrange remainder. Now here I'm just writing this expression here, and I want to compute the integral. Now here I would like to use again the integral mean value theorem, but I have a small problem, and that small problem is that I really need this function to be positive between a and b. But now it's not, because you see here I have positive x squared. So that means that I have, let's say, if this is a and this is a b, that means that my polynomial, if x squared is positive, that means it has a minimum, yeah? So that means my polynomial looks like this. So that means between a and b, which are the roots of this parabola, the function is negative. So I would like it to be positive, and it's not. How can I arrange that? Well, I will just multiply this term here. I will multiply it by -1. Okay? Multiply by -1. And I will also multiply here by -1. Okay? So in that way, I have this minus that comes from this product, and this minus switches this x minus b to b minus x, and now this polynomial is this one. You can see that now this it should be a parabola, okay? Now this is minus x squared, yeah? So if this the higher degree is coefficient is -1 minus x squared, that means that we have a maximum. So it looks like this, because the zeros are also a and b. So now this is a positive function. This now is a positive function, and we can apply the intermediate, the integral mean value theorem. Okay, so this is the positive function. It remains inside the integral, and this guy can be written outside the integral at a point that I don't know, C, but I know it lives between a and b. Now, the good thing is that I can compute this integral. That's very simple. It's a polynomial. I compute the integral, and I get this. So if you like boxing things, this is what we need to box. This is the formula that we obtain to express the integration error for the trapezoidal rule. I think it's very important always to bear in mind that this psi function lies inside the interval a and b. Okay, that should be always beared in mind. We could do exactly the same for Simpson's rule. I will not repeat it again. In fact, it's a little bit more complicated, and it is out of the scope of this course to really understand it. But I will just say that the formula for the error for Simpson's rule is this one. So let's box it. And again, it is very important to bear in mind that this psi value that appears here is this psi value lives inside the interval a b. Okay, so we can summarize what we did. Now we have these red formulas. Yeah, we have the expression of the integration error for each one of the simple rules we know. Okay, now something that is very important to note here: what would happen if I try to compute the integral of a degree 0 polynomial using the rectangle rule? Well, what would happen is that if my function f of x is a degree 0 polynomial, so that means this is a constant value, then of course f prime of x is going to be 0, yeah? So that means that f prime is going to be 0, and this error is going to be 0, and that means that the rectangle rule is capable to compute exactly integrals of polynomials with degree 0. That makes sense with the geometrical point of view of the method. Yeah, if I have a constant, if I have a constant polynomial and I use the rectangle rule to compute an approximated value of the area between A and B, of course I will compute the exact value under this line, because I will approximate it with a degree 0 polynomial, so the approximation is going to be exact. So that really makes sense. Yeah. Now, the same thing with the trapezoidal rule. As I'm using with the trapezoidal rule a degree 1 interpolation, then the method is capable to compute exactly the integrals of degree 1 polynomials. If I use here as f of x a degree 1 polynomial, I know something like let's use another letter here, cx plus d. Yeah. Of course, f prime of x is going to be c, and of course the second derivative is going to vanish, it's going to be 0. So in this formula, f prime prime is 0 always, and this error is 0. So the trapezoidal rule, as expected, it's capable to compute exactly integrals of degree 1 polynomials. Now, what is really something unexpected is that Simpson's rule is able to compute exactly integrals of polynomials with degree 3. Now, we were expecting here degree 2 because Simpson is using a parabola to approximate the function. So, of course, it's obvious that it must compute exactly the integral of parabolas, but it happens to have this so-called superconvergence, and it's capable to compute not only exactly the integrals of parabolas, but also of cubic degree 3 polynomials. Okay? So we can see here, this is the first derivative, this is the second derivative. Yeah, in the formulas for the rectangles, it's the first derivative. For the trapezoidal rule, I have the second derivative, but for Simpson's rule, we have the fourth derivative. So this is really unexpected, and this is sometimes called superconvergence, and this really means that Simpson's rule is paying off for more than we were expecting. Okay? Now, I've been talking here about exactly integrating polynomials using numerical methods. Why I'm doing that if I can compute exactly with analytical methods the integral of a polynomial? Well, because normally we use polynomials as a reference. The higher the degree of the polynomial we can compute exactly, the better we assume is the method. The more complicated is the polynomial we are able to compute the integral exactly, the better we think is going to be the method, because it can deal with more complicated functions. Okay, so that's the reason. Now, I would like to do an exercise to make sure we understood what we are talking about here. Now, let's consider the function, this is wrong, let's consider the function x cubed, okay, x to the power 3, in the interval 0, 4. And the proposed exercise is to compute the approximation of this integral of this function x to the power 3 between 0 and 4, using all the simple rules we saw, and bound the error in each case. Okay, this should be in English. Bound the error in each case. Okay, bound the error, okay, in each case for each method. Okay, let's try to do this proposed exercise. Okay. First, we write here the proposed exercise. We want to compute the approximations of this integral between 0 and 4 of this function, and using all the simple rules we saw, and bound the error in each case. Okay? Now, in order to solve this exercise, I think it's a better idea to show the previous slide, which has the summary of all the needed formulas. Okay, I think it would be better. Okay. Now, let's start with the rectangle rule. When I use the rectangle rule, I know that the exact integral is approximated by h times f of a. Okay, so I will approximate the exact integral by h times f of a. Now, remember here that h is b minus a. Okay, h is b minus a, and f of a, and we will compute b minus a. Remember that 0 is a, 4 is b in this case, and f of x is x to the power 3. So we will just evaluate this and get 0. That's the approximation we got for the rectangle rule, which is a really bad approximation. I know that. This is going to happen with all the simple rule methods. We will improve this in the next lecture with composite rules, but for today we will leave it like that, okay? I know it's a very big error. However, we can try to bound the error. Here, I know that the integration error looks like this. It uses this formula, so I know it follows this formula, where psi, I don't know the value. I don't know where I should evaluate this function, but I know that it lives between 0 and 4. Let's use that, okay? So here I'm just computing f prime. Now, the derivative of x to the power 3 is 3 times x squared, in this case psi squared. H is equal to 4. We do the calculation, and now I want to bound this. How can I bound this? Well, the only thing I know is that psi lives inside the interval 0, 4. So the highest value possible in this case is when psi is equal to 4. So that's the higher bound, the upper bound of the error. Let's do the same thing with the trapezoidal rule. Now, for the trapezoidal rule, I know that this formula is giving me the approximated value of the exact integral. So I will use this formula. I will substitute in here h by b minus a, which is 4 in this problem. f0, fb is f at 0.4, and we will do the calculations, and we will get that 128 is the approximated value of the integral, which still has a lot of error, I know. And we can bound the error. Now, the error comes from this formula, okay? So I need to use the second derivative of the function. The second derivative is 6 times x, or 6 times psi in this case. H is equal to 4. We do the calculations, and we get this. But I don't know the value of psi, but I know it lives in the interval 0, 4. So an upper bound would be, an upper bound of the error, the maximum value of the error is when psi is equal to 4. So that's why we bound the error by this value. And finally, we use Simpson's rule. We apply this formula that we obtained in the previous lecture. H, remember that h is b minus a, okay? That is very important. When using Simpson's rule, we have this interval a and b, okay? And we are using an intermediate point that is xm. But remember that the distance between a and b is what is called h, okay? Not the distance between a and xm, okay? H is the whole distance between a and b, okay? So that's why here h is again equal to 4, okay? Xm in this case is 2, yeah? Because a is equal to 0, b is equal to 4, the intermediate point is 2. So xm is equal to 2. We do all the calculations and we get 64 that you can verify, but this is the exact value of the integral. And in fact, when we compute the error using the formula here of the integration error for Simpson's rule, you see here we have a fourth derivative. And what happens is that if we get f of x equal to x to the power 3, the fourth derivative happens to be 0. So, of course, this is 0. 0 times whatever is 0. So, it's telling us that there is no error. This is the exact value of the integral. And that makes sense because f of x in this case is a degree 3 polynomial. And we know that Simpson's rule is capable to compute exactly the integrals for degree 3 polynomials. So this really makes sense. Okay? So that's what I wanted to cover today. In the next lecture, we will talk about composite rules. See you there. Bye-bye.